Our next type of polynomial we'll be factoring is called binomials. When factoring two-term polynomials, which we call binomials, you must use a formula. There are three formulas that we're going to be covering today. The difference of squares, which is a squared minus b squared, the difference of cubes, which is a cubed minus b cubed, and the sum of cubes, which is a cubed plus b cubed. Notice the cubes indicate that we're going to have little threes. The squares indicate we're going to have little twos. Difference means minus and sum means add. So these names are very descriptive of their polynomials. So for the difference of squared polynomial, we have a squared minus b squared is factored into a plus b, a minus b, and that's its formula. You will need to memorize all of these formulas. The next one is difference of cubes. We're going to be talking about a little bit later. Factors in a minus b times a squared plus ab plus b squared. And a cubed plus b cubed factors into a plus b, a squared minus ab plus b squared. You will need to memorize all three of these formulas, but I will show you some shortcuts to memorize those. I need you to notice at this point that there is no formula for a sum of squares, which would be a squared plus b squared. We have sum of cubes and difference of cubes. We have difference of squares, but we don't have the sum of squares. I need you to understand that a squared plus b squared cannot be factored and is considered prime. If there was a formula for it, I would give it to you. I'm not hiding it from you. There is no formula for sum of squares. It actually just doesn't factor at all. Now when factoring a difference of squares, you should remember these perfect square facts. 1 squared is 1 times 1 or 1. 2 squared is 2 times 2 or 4. 3 squared is 3 times 3 or 9. I'm just going to go ahead and finish this chart out. I'm assuming that most of you remember these, but it's a good time right now to review them because these are the numbers that are perfect squares and we will be using for difference of squares. Now the last column is where people start not remembering these. 13 is 169, 14 squared is 196. I kind of remember these two together because 169, 196, the last two digits are just interchanged. 15 squared is 225, it comes up an awful lot. 25 squared, the last one, is 625. I kind of have these, I memorized these two together. 15 is 225, 25 is 625. 16 squared comes up an awful lot as well. That's 256. You might remember that because you see it usually in your computers like 256 megabytes or kilobytes or processing speed or whatever. 256 is one of those computer numbers. Comes up an awful lot because it's a power of 2. And then 20 squared also comes up an awful lot. 20 times 20 is 400, which I think a lot of you probably know because 2 times 2 is 4 and just add 2 zeros. Notice I skipped 17, 18, and 19, and 21 through 24. Those don't come up an awful lot, but 20 and 25 do, so I just thought I'd give you the ones that come up an awful lot. Next, we're going to be factoring using the difference of squared formula. So I went ahead and put the formula again right here close so you don't have to keep flipping. Don't forget that you might need to look for a GCF. If you can ever find a GCF and factor it out, it's going to make your problem a whole lot more simple, and you always wanted to try that first. On the first problem, 25x squared minus 81y squared, there is no GCF here, but I can rewrite both of these terms as a difference of squares. See the 25 and the 81, that's a big tip-off that we have perfect squares. Those are the numbers that we just kind of listed. 25 can be rewritten as 5 squared. 25x squared can be rewritten as 5x times 5x, or 5x quantity squared. 81y squared can be rewritten as 9y squared. So now the 5x is kind of like my a being squared. My 9y is kind of like my b being squared. And my formula says a plus b and a minus b, which means the 5x goes in the fronts of both my parentheses. The 9y goes in the backs of both my parentheses. And my signs are just one of each. This is probably the easiest of the three formulas to memorize. It's just a plus b and a minus b. Students often really do well with this formula. So on the next problem, do we have a GCF? Well, no, you can't ever have a GCF with 1. So I'm going to see if I can rewrite it as something squared minus something squared. It is a minus, so we do know that this is factorable. 16x squared can be rewritten as 4, because 4 times 4 is 16, x squared, because x squared squared is x to the 4th. So 4x squared times itself 4x squared truly is 16x to the 4th. Now 1, sometimes students forget about this, but 1 is a perfect square. It's just 1 squared. So we have 4x squareds going in both of the fronts of my parentheses. My 1 needs to go in both backs of the parentheses. And one term needs to be positive and one of them needs to be negative, and I have factored this. Now, well, my last problem, I was done at this point. But this problem is not quite done, and the reason it's not quite done is because the second parentheses is another difference of 2 squares. 4x squared is a perfect square, that's 2x times itself 2x. 1 is a perfect square, that's 1 squared. So the second term can actually be factored into 2x plus 1, 2x minus 1. That's the second factor. But what happens to this first red factor? Well, that's a sum of squares. We just said a sum of squares doesn't factor anymore. So that sum of squares just needs to come down. And now this is completely factored. The sum of squares can't factor anymore, 2x plus 1 can't factor anymore, and 2x minus 1 can't factor anymore. Now I am completely done. Some students might look at this and say, well, if that can keep going, how come 5x and 9y can't keep going? Well, 2 reasons. First of all, there's no squares up on the x and the y, and 5 isn't a perfect square. So yes, this second problem kept going. It went twice. It had 2 difference of squares, but that doesn't mean it's going to infinitely keep going. It only worked because we started with an x to the 4, which left us with x squareds inside, which allowed possibility for another difference of squares. On my next problem, I have 2x squared minus 50. Now, 2 and 50 are neither of those numbers in my list of perfect squares. So this is a dead giveaway that we might be needing to look for a GCF. So when I factor out a GCF, I'm getting 2 out of both of the terms, which leaves me with x squared minus 25. And x squared minus 25, that is a difference of squares. That's x is being squared on the first term, and 5 is being squared on the second term. So that leaves me with x's in both fronts of the parentheses, 5 in both backs of the parentheses, with one sign positive and one sign negative, and that is completely factored. Now on the next problem, this might look a little scary because we have a binomial being squared, but that binomial, this whole part is just like the a. The x plus 2 is kind of like the a squared in my formula. So it's already squared minus something else squared. How can I rewrite 9 as a perfect square? Well, that's just 3 squared. So in this problem, the x plus 2 needs to go in the fronts, and the 3 needs to go in the backs, and my signs are one of each sign, one positive, one negative. Now this kind of looks like it's done, except I can simplify, because x plus 2 plus 3 is really x plus 5, and x plus 2 minus 3, well, that's just really x minus 1. And this is my factorization of my original polynomial. The next problem is very similar. We have 3x minus 2y is already quantity squared. On the second term, I have 49z squared. Well, I can rewrite that as 7z quantity squared, because 7z times itself, 7z, is 49z squared. In my answer, the red 3x minus 2y goes in fronts, in both fronts. The 7z goes in both backs. And my signs are one of each, one positive, one negative. Now if I could combine any like terms or factor anything else out, I would, but I can't because each term has an x, a y, and a z, and they're each different, so I can't actually keep going. On this next problem, it looks like I may have a GCF right in the beginning. So you see this 5x plus 4 and this 5x plus 4. I'm going to factor that GCF of 5x plus 4 out, and then I'm left with x squared minus 9, and that one GCF made that problem look a whole lot more simple. Now that it's rewritten like this, I can clearly see that the second term is a difference of squares. So we have 5x plus 4. The second parentheses is going to turn into 2. So I have x in the fronts, and I have 3 in the backs, and then my signs are just one of each. And that's my final factorization.